Okay, let's talk about rational functions, particularly in how it's going to be used in calculus, right? So in calculus, we're going to use a lot of new techniques to find out even more things about functions very quickly. So we're going to be able to find out when functions turn around, for example, a max or a min. We're going to learn about concavity, the shape, when does it change, concavity and shape. But we have to start with a really good foundation about rational functions and what they look like roughly. So I want to give you like a 15-minute quick overview of rational functions, how to look at them, and kind of get a feel for what the general shape is. Now, there's all kinds of rules you probably learned in PreCalc, and those are fine. Like the highest power term in the numerator is one power higher than the term in the denominator, and that's what these 5 examples are kind of showing, is those different conditions. But rather than memorizing rules, and I tend to forget rules myself, so I'd rather just teach you and show you to look at the function and plug big numbers in, right? Like a million or negative a million, and see what happens. And to look at the function and ask yourself, what's really happening here? So that's actually the first thing I'm going to do. So I'm going to show you with a highlighter here that this first rational function, remember ratio, rational function is a fraction, right? It means there's a function at the top and a function at the bottom. So what's really happening here, even though we might not talk about it enough, is you're taking the yellow function and you're dividing it by the green function. Well, what happens if you took a cubic function divided by a linear function, right? A cubed power divided by a first power, a linear. You should get a quadratic. And in fact, you do, roughly, right? You get roughly a quadratic shape. So over here, we're gonna write that, right? So we're gonna write quadratic. If I can pick up the right pen. Now, there's some funky stuff going inside. In fact, there might even be a vertical asymptote, right? We don't really know. It's hard to factor a cubic, so I'm not going to go into that much detail. But the basic shape is going to be quadratic, and in the middle, some wiggling is going on, right? So I'll talk about that wiggling in a second. And in the second example, it's much easier to see exactly or closer what's going on in the middle. Now, in the second one, it's a what? Quadratic, a parabola, divided by a linear. Well, what should a quadratic divided by a linear give you? You guessed it, linear, right? So what does that mean? That means it's going to have a slant asymptote, right? Or it's going to be, well, we'll put a question mark there because actually it's a little different than that. And I wanted to use yellow. Okay. So for the third one, we have a quadratic divided by linear again, and we're guessing maybe that's a slant asymptote. We'll take a look at that in a second, but it's definitely going to be linear in nature, right? And what we're really saying here is especially at the ends, right? In the middle, I'm not so sure what's going on, right? There's some wiggling going on. There may be vertical asymptotes, which we can spot pretty quickly, actually. But I know at the end it's going to basically look like a line, and it'll never actually reach there. That's what we're talking about, asymptotes, right? It'll never actually reach the linear shape, but it will come very, very close to it. Now this one is a quadratic divided by quadratic. Now what happens when you divide anything by itself? Even though these two functions aren't identical, they're identical in nature, right? So if you divide a quadratic by itself, I'm not really sure, but I'm guessing 1, right? I'm guessing 1. Now, of course, if there was a 2 here, if this was 2x squared and I divided 2 by 1, I might write a 2 here and that would be accurate. But basically, the idea is I'm not getting a diagonal linear, right? I'm going to get a horizontal linear, right? So if we want to jump the gun a little bit, we can just say this is a HA, horizontal asymptote. Okay, and then the last one is a quadratic divided by a cubic, right? Quadratic divided by cubic. So here's where I'm going to actually start talking about putting in big numbers, right? So let's go to another slide with the same functions on here, and let's take a look at what would happen if I put a big number in. So let's put in like x equals 100 into this guy, right? So that means I'm going to put 100 in here, I'm going to put 100 in here, and I'm going to put 100 in here, right? And what do I get? Well, what I get is I get a pretty big number on the top, but a much bigger number on the bottom, right? So I get 10,000 here, but 100 cubed, right, is a million, right? A million. So this is 10,000 plus, really don't care, 506. That's not very big. And this is a million, right? So that's a very small decimal, right? And if you think about it, if we ignore, and that's the key here that I want to talk about today, if we ignore plus who cares divided by x to the third plus who cares. Now, why am I writing who cares, right? It does make a difference. But what we're saying is these terms here, these three terms, really, as x gets really big or very negative, right? Very big negative number or very big positive number, these really don't have any major effect. In other words, it's roughly equal to this. When we talk about limits, we'll say the limit as x goes to infinity, right, is equal to that. And what is x squared divided by x to the third? Well, x squared divided by x to the third is just what? 1 over x. And what happens if you put a really big number like a million in here or even 100 in here? You get 0.001, 0.0001, a really small, really small number, okay, which is about 0. So if I go back to this page, the first page here, what we're going to say is, yeah, this is a horizontal asymptote also. When you put in really big numbers, negative or positive, you really get something close to 0. So I could put linear here. They are linear. They're just horizontal. Okay, so that gives me a basic feel. If we were to graph these right now in Desmos, and I have graphed them, so we'll take a look at them, I kind of know that this is going to be like a big U with some stuff happening in the middle. I know that this is going to be linear in nature with maybe some stuff happening in the middle. I know that this is going to, at the ends, right, approach 1. And after I do the vertical asymptotes, after we factor a little bit and we'll take a look, we'll actually draw the dotted lines to show us where the borders are going to be, right? Okay, now this guy maybe factors. I'm not going to spend a lot of time doing it, right? So I'm not really sure, but I'm guessing at x equals -4, I'm guessing that x plus 4 is not a factor here. So I'm guessing at x equals -4, there's a vertical asymptote. Okay. And here, I don't know, I got a factor, and this is easily factorable, so let's do this. So this is x plus 4, excuse me, x minus 2 over x plus 4. Okay. So this reduces, and what I'm left with, right, what I'm left with is y equals x minus 2. What is y equals x minus 2, right? It's a line. It's a line that has a slope of 1, because this is 1x minus 2, and a y-intercept of minus 2. So if I wanted to draw that, I would do something, that's not a good one, so I'm going to move it down a little bit, like that. Maybe that's better. Okay, so it passes through -2. It's got a slope of 1. So this purple function here, y equals x minus 2, actually this whole rational function should look like this almost everywhere with one small problem, right? When you have a whole that reduces, when you have two factors that reduce, you actually get a whole, right? X equals, whoops. At x equals -4. So even though you reduced the original function, still you're not allowed to have a -4 in here. That will produce a 0 in the denominator, which is trouble, which is why I know x is equal to -4 is going to be a whole, right? It's a whole. And hopefully that rings a bell from PreCalc. So it's basically that green line with a little hole there. Desmos won't show us. When we go to graph this, even on the graphing calculator, you won't see the hole. You'll see the line, but we know there's a hole here. Okay? This function is quadratic in nature. I know that x cubed divided by x is equal to x squared, so I actually know that the basic shape is going to be something like this, right? I could find the zeros if I wanted to. I don't know if it's going to actually pass through the x-axis or not. but it's going to do something. And then in the middle, it's going to wiggle, but eventually it's going to go back up again. Right? And I don't know what's going to happen. There may be a vertical asymptote. It may just wiggle a little bit. I don't know. But I know what's going to happen at the ends, and that's really the point of what I want to get across here is just basic shapes, right? Now this guy does not reduce, right? This is x plus 3, x plus 2. So there is no reduction. There's no hole, right? There's no hole, but there definitely is a vertical asymptote because you can't have a 4. If you put a 4 here, we're in big trouble. Okay, so at x equals 4, I'm putting a dotted line, meaning as I approach this line from either side, I'm going to hit infinity, right, or negative infinity. And we could test that by plugging points in. I'm really not going to spend a lot of time today doing that. You could plug some points in. You could also, of course, see that there's going to be zeros because the numerator will be 0 at -3 and -2, right? So I don't want to spend a lot of time on this, but at -3, x equals -3, and at x equals -2, right, it's going to be 0, right? The y is going to equal 0, as long as it doesn't interfere with the denominator, which it doesn't. So I kind of know some stuff's going to go on here. But I do know that this is going to be linear in nature, okay? And I can actually find this. I think it's worth the time to do it. We'll divide these two numbers, right? We'll actually see what we get when we divide those two numbers. But I know, without even doing that, I know it's going to look something like this. And maybe we'll adjust it when we come back, right? So there's going to be some slant asymptote like this. I'm assuming y equals 0, b equals 0, but I'm not sure. It could be here, it could be down here, right? But there's going to be a slant asymptote. It's going to have a slope of 1. Actually, I'm not sure it's going to have a slope of 1, so probably going to have a slope of 1, but we'll take a look, okay? Well, I do know, but I'll explain why I know in the next slide. Okay, so let's actually take the time to do that. So, because this guy was easy, he had a hole, but he was basically a linear function with a hole. But this guy is not, because this does not reduce, right? So let's actually divide x minus 4 into x squared plus 5x plus 6. I'm going to go real quick here, so maybe I'm not that quick. Don't forget to change the signs. You get 9x. And really that's all I care about because x goes to 9x 9 times, right? Plus 9. So it's going to do this, and then the rest of this is going to be plus or minus some fraction that we don't care about because x plus 9, right, is the line that it's going to asymptote toward. All right, so we go back to my previous slide. I'm actually going to raise this. Oh, it's going to widen up to 9. So again, the scale could be off here, but it's going to be. I'll make that 9 right there, and then here. So what's going to happen? Well, there's a few things that could happen, right? The function could be up here and down here, right, like that, or it might be here and here. Okay, it'll never hit these 2 points that'll approach it, but as you go further and further and further, it's going to be really close to this black dotted line, meaning further to the right and further to the left. Now this guy, right, when we put in big numbers here, like we put a million in, we're going to get a million squared plus who cares, divided by a million squared minus who cares. So not that it's going to be equal to this, but it's going to be really close to a million squared divided by a million squared. What's a million squared divided by a million squared? Y equals 1, right? So it's a horizontal asymptote at y equals 1. This is going to get really, really close to 0. So we have a horizontal asymptote at y equals 1. And we have a horizontal asymptote at y equals 0. We have a vertical. I'm just going to go quick here because I think you know how to do these already. We have a vertical here at, oh, actually, I got to be careful. That's not true because the numerator does factor. So let's do that, right? So this is, again, x plus 3, x plus 2, and this is x plus 2, x minus 2. So I got to be careful. There is a hole at -2, right? And there is a VA still at x equals 2. So it's a rather complicated function. So at x equals 2, there's a VA. And I'm going to ignore the hole for now, but somewhere over here at x minus 2, there's a hole. It just disappears. Okay? But I do know, no matter what the function does, right, it's going to approach this line. So I'm guessing, and there's, of course, ways to check. Maybe it's like this, and maybe like this. Right? Could it be here and here? It could be. All you have to do, really, is find the zeros of the function, right, which is going to be -3. So actually, I know this passes through at -3 because I set the numerator equal to 0. And I can plug in a point. So you can plug, we know that this vertical asymptote is at x equals 2. So at 3, what happens here? Is it above the line or below the line? So if you plug 3 in here, I think you get something like 9 or something, but or 6 or whatever, but it's way up here. It's above the line. So I actually do know that that's the shape just by testing 1 or 2 points, right? Pretty easy. And this guy here, I'm not going to spend a lot of time on it. X cubed plus 2 may be factorable, maybe it has vertical asymptotes, whatever. But all I'm just trying to get to the point here is that it's going to approach 0, either from the top or from the bottom. And of course, if we plug some points in, we could see. And it might wiggle in the middle. It might have vertical asymptotes. I don't know, right? But it'll come back to these two lines. But at least I know the end behavior. And I can spend more time talking about finding the zeros and everything else. But just to give you a basic feel of what I expect you to know by just looking at a rational function, thinking about what's being divided by what, plugging in a couple of numbers, usually big numbers like infinity, you get a great feel for all these functions. So let's take a look in Desmos and see how accurate we were. So we were predicting a parabola with some kind of funky stuff going on in the middle. Funky is an official math term, at least in my class. So let's, whoops, that's infinity there, sorry about that. Let's take a look. So here's the first graph, right? And you can see it's a pretty big graph, so you have to really zoom out far. It comes down like this, comes down like this, and where the parabola would normally have a vertex, it does a little twist. See, it goes down, and there's actually a vertical asymptote somewhere here. But eventually it picks up from infinity, comes here, and it goes back up. So here's the parabola part, right? From here, from infinity, from positive infinity, it comes down. It does the wiggle, it does a vertical asymptote, it does some funky things, but then it comes back up again. So the basic shape is still a parabola with weird stuff happening in the middle. But we were right when we guessed about the parabolic shape, right? So here we said it, or quadratic, we said it was quadratic. So it looks like a parabola. The next one should look like a linear function, right? And with a hole, we're not going to see the hole, so we just should see a line, and we do, right? So if I go here, turn the first one off, there it is. And it's zoomed way out, so we're not going to really see the y-intercept too easily. There we go. Okay, exactly what we expected. You're not going to see the hole at -4 right here because Desmos thinks it's infinitely small, and therefore it's not going to show it. And it's right in a way, right? The third one, we know it's going to have a slant and it's going to have a vertical, so it's going to do one of these two things, right? Maybe this one and this one. Let's take a look. And sure enough, there it is. So you can't, again, you got to zoom out to see the whole graph, but there it is. So it's basically approaching this line, which I think was x plus 9, whatever we turned out to be, as you get closer to infinity on both sides, negative infinity, positive infinity, and there's that vertical asymptote that we also predicted, right? Right there. This one, I think we're exactly going to look like this, right? These two black curves here. It's going to look exactly like that, I'm pretty sure. Let's take a look. So some of these are obviously easier to see than others. And yeah, that's it, right? There it is. I mean, again, if you zoom in, it'll look a little more like our graph. So there it is. We predicted this, and we see this. Okay, good. And then the last one we didn't spend a lot of time on, but the last one, we know it's going to approach 0. That's the main thing on both sides. And then it's going to do some funky stuff in the middle, which I'm not really sure about because I didn't feel like factoring the cubic. So let's take a look at the last one. And that's exactly what happens, right? You can see it's horizontal asymptoting at 0, but it's doing some wiggle. There's even a vertical asymptote here. If I had factored, I may have found it. Does a little wiggle here. But we're going to use calculus to find these things, actually. Calculus will help us predict these peaks and valleys, these mins and maxes here, and it will actually predict this point too, where the concavity, the bowl up and bowl down, you'll hear me talk about that in calculus a lot, where that changes. So we don't really need to know much more than what I just talked about or hinted at with these rational functions, because calculus will do the rest. But when you go into my calculus class on day 1, I expect you to have a working understanding of rational functions and what they would basically look like. So we're ready to go. Thanks.